Hello. We're waiting for more people in the audience to join. We'll get started at about 4:25. Okay, we're going to get started. So welcome everyone to the Headwaters Research Experience Summer 2025 cohort. We have many students this year who've worked really hard through the summer to formulate questions on topics that they were excited about, to work on hypotheses, to figure out how to do an experiment in the time frame of just a summer, to adapt their methods to work for all kinds of different constraints, to collect their data, to interpret their results, and now to share their results with you. After this, they'll also be completing their manuscripts and they'll be submitting those to the Headwaters Journal. I'm the head instructor for this summer's research experience course. My name is Leslie McGinnis, and I am proud to introduce our first group of mentor and student. For each group, we'll have the mentor introduce the student, and then if some mentors can't be here, then I will be introducing that student. But for our first student up, we have Vihan Reddy and his mentor, Sean. So I will add Sean to the stage here.
Hi,
and
thank you,
remove
Leslie.
myself.
Yeah. Okay. So it's with my pleasure to present Vihan. We have worked together for the duration of this class, and I'm going to let Vihan discuss why this topic was chosen, but it's a very interesting topic, and I think we've learned a lot in the progression of, progressing in science as far as how analyses and different analyses with various results and things can be combined and put together. So without further ado, I will turn the stage over.
Hi, I'm Vihan, and this is my presentation for the effects of genetics and the consumption of ultra-processed foods on obesity. So to begin with, over the past few decades, obesity rates have risen dramatically, with US adult prevalence climbing from 14% to 42% since 1980, and with similar trends in children. One major contributor is the growing consumption of ultra-processed foods, which are high in sugar, fat, salt, and additives, but are low in essential nutrients. And this has been linked to weight gain and metabolic disorders. At the same time, genetic factors such as the allele of the FTO variant can also increase susceptibility to obesity, partly by promoting loss of control eating and a preference for energy-dense foods. Understanding how UPF consumption interacts with genetic predispositions, like the FTO variant, is key to developing effective, personalized nutrition advice and targeted public health strategies. This study tests the hypothesis that carrying the allele of the FTO gene interacts the obesogenic impact of ultra-processed food consumption. While previous research has looked at UPF intake and the FTO variant separately, my goal here is to examine their combined influence. I focused on whether individuals with the AA or AT genotype were more likely to develop obesity from high UPF intake compared to those with the TT genotype. By comparing obesity prevalence across these groups at different UPF intake levels, I aim to identify a potential gene-diet interaction. I found studies on Google Scholar using keywords, such as the name of the gene I was looking for, genetic factors, obesity, and ultra-processed food. I collected relevant p-values from the studies and used Fisher's method to get an overall p-value. Fisher's method is a mathematical function to combine several p-values into one, providing a single value to represent whether the hypothesis was correct. I ran a meta-analysis to explore how ultra-processed food consumption and the allele of the FTO gene variant that affected obesity risk in children and adolescents combined. I searched Google Scholar for peer-reviewed English language studies involving participants aged 0 to 18 that tested for the allele, measured ultra-processed food intake, and reported obesity markers like BMI. The 5 studies in this meta-analysis all point to a consistent link between the FTO gene's allele, ultra-processed food intake, and obesity in children. Kwan's meta-analysis found that the allele significantly increased obesity risk, while Rifo's study showed that each allele raised obesity odds by 42%. Hierman's trial linked higher UPF intake in early childhood to higher BMI z-scores, and Yang's study found that TA or AA genotypes carried greater obesity risk than TT. Finally, Molina-Luke's research showed that AA genotype children had the highest body weight and prevalence of metabolic syndrome. Together, these findings suggest that the allele can heavily amplify the negative metabolic effects of high UPF intake. This graph represents the overall findings and the change of BMI for one of the studies. As time continued, more UPFs meant that the study's participants' BMI would increase, but it's unclear how much the time frame and ages of the participants affected this. While this is the overall graph for the study, within the study, while there was an observed gap for 3 and 4-year-olds, there was nothing observed for 5-year-olds. This chart shows how BMI varies by genotype. The z-score is highest in participants with the AA genotype, followed by TTA and then by TT. TA is significantly higher than TT, and as a baseline, the TT group is about 2 standard deviations above the average, as all participants in this segment of the study were obese. The data shows a strong gene-environment interaction, with a highly significant p-value. These children may be more likely to eat high-calorie, low-nutrient foods, leading to more fat storage and early health problems. However, there are some limitations, as many studies relied on self-reported diets, which aren't always accurate. Additionally, the number of studies was small, and differences between populations might affect how widely we can apply the results. Some studies didn't consider important factors like socioeconomic status or physical activity. With UPF intake rising quickly among kids, this research shows that those who are genetically at risk may need more targeted support. Even once the study was complete, it brought up even more questions. How exactly does the gene modify brain signaling so people are more likely to eat fat-heavy foods? Are there other genes that interact with UPFs in similar ways? Additionally, it's still unclear whether this interaction remains the same throughout all ethnic and genetic backgrounds, as certain ethnicities could potentially be less or more affected. Knowing at what age early dietary interventions are most effective could also be helpful, and using biomarkers could potentially lead to more accurate studies. Finally, using genetic screening in obesity prevention programs could lead to more targeted care. I would like to sincerely thank my parents and my brother for their constant support, encouragement, and patience throughout this project. My research was only made possible by them and their help along the way. And finally, these are my references. So thank you for listening.
Wonderful job. Thank you so much. Can we have any questions from our audience? You can put them in the chat and I can read them to Vihan. I'll also add Sean in case he would like to ask a question.
Yeah, I can ask one. All right, so Vian, let's talk with this and using other markers and things moving forward. You know, I guess what do you see kind of as the future for some of these studies? Have you thought about that at all? It's kind of a tough question, right? It's not, and there's no one single answer, but just as far as from the sources that you found, right? Like there's a lot of different sources, a lot of cool information out there about this. Any thoughts on kind of going to that next step?
For the future, I see it as being like examining exactly how this gene affects brain signaling. So we know that it affects people, but we don't know exactly how it does that and the mechanisms. So I think that'd be really interesting to study.
Exactly right. Like it leads to a lot of different openings, right? For this is not just your diet and consumption, but we always say you are what you eat, right? So exactly. Yeah, great answer.
See
Yeah.
if there's any others.
So would there be a better metric to measure weight gain rather than BMI, since flaws have been found in the BMI? Yeah, yes, there are many different weight gain metrics, such as waist circumference as an example. I just found that BMI would be well, many studies use BMI, and as this was a meta-analysis, I was using those studies as sources along with their p-values. Um, but with the BMI, I could have used waist circumference, I just found that BMI was the most common kind of metric, so it was the easiest to use.
Great. Thank you so much. All right, let's give a big round of applause again. I mean, digitally. Wonderful job. And we're going to set up our next member of the class. So I would like to turn this over to our longtime mentor, Jesse Scott, to introduce Amanda.
Hi, my name is Jesse Scott. I am excited to work with Amanda during this semester, and she has done a fantastic job of studying these effects that you will hear about tonight. And I'm looking forward to seeing Amanda accomplish great things in the future. In addition to this research, she is also pursuing an Eagle Scout project concurrently at the same time. So she's got a lot going on, and she's done an amazing job, and looking forward to this.
Okay. Hi, my name is Amanda. And for my project, I'm researching hazardous algae blooms and like the factors of that. So for context, I was studying cyanobacteria, which is blue-green algae, and it is the main problem in freshwater bodies in freshwater. Dinoflagellates are in saltwater, and so algae is found in all 50 states, plus some territories, and I focused on Quarry Lakes Regional Recreational Area, which is pretty near my house. And during the pandemic, my family and I would often go fishing, and we often went to Quarry Lakes, and so I saw signs that said, like, don't go to the water, don't interact with the water, because of the algae blooms and how that's toxic. And so naturally I was curious about, like what caused algae blooms. And so here are some of the signs that I've seen. You can see on the left, it has warnings about algae blooms and what to do. And then it has rules that people should follow. And so for my project, we decided to research again, like the correlation between factors such as temperature and dissolved oxygen, and how that affects algae blooms, or how that is related to algae blooms. So we know that we already know that algae bloom is affected by temperature, and that varying temperature varies the amount of growth, or it varies the toxin level in the water. And we know that dissolved oxygen is also related to algae blooms. And so for this project, I've had to first get the data. And so I emailed a bunch of different lakes to see if they had data that I could use for this project, because since the algae is toxic, it would not be safe for me to go out and collect my own data. So I emailed a whole bunch of lakes to get information on dissolved oxygen levels, water temperature, and algae concentration. And then I finally got a data set, multiple data sets from Quarry Lakes. And so dissolved oxygen was on one spreadsheet, and temperature was in the other spreadsheet. So I had to combine those two spreadsheets and to line dates and variables. And then once I had like one spreadsheet, I put that into an R script for processing, and then we connected an analysis to see if there was a correlation, and we found that there was. And so then we drew conclusions about the water quality. And here you can see the giant spreadsheet. It has date on the left, and then on the far right hand side, it has dissolved oxygen and temperature. And these are, you can see there's multiple locations for the same day, for some days. So for example, the boat launch or at the swim beach. And here's our first graph on dissolved oxygen. And we can see that as the dissolved oxygen increases, so does the average toxin. And ppb means parts per billion. And you can see that it's a linear regression. Here is the monthly average for that, and it's the same data points, but you can see how it really varies. And even though there is some slight variation, it still starts lower and ends up higher. Here's the temperature, so we can see that as temperature increases, the average toxin levels decrease. And again, it is parts per billion and is a linear relationship. And here we can also see that the same data points over the monthly average. And here are the monthly averages for hazardous algae blooms and water quality. And we can see clearly that between May of 2020 and August of 2020, there was a large spike in toxin levels, while dissolved oxygen remained roughly the same. And temperature, as expected, went up and down depending on the month. And on the y-axis, the values are standardized, which basically means that the values are relatively close to each other, or relatively similar, so we can standardize. Here is the same graph but zoomed in, so from August of 2020 to March of 2022. And our original data set went from 2020 to 2022. And so this is the data that we have for that time span. And we can clearly see that there was a larger spike towards February 2022 to March 2022, as opposed to after May of 2021. And so these are the seasonal patterns. The black dots are outliers, and we can see that the dissolved oxygen is consistently lower than the temperature, and that there's like a larger range for the temperature during fall to spring. Here we can see that seasonal toxin concentration is much higher in spring and winter and much lower in fall and summer, although there are some extreme outliers in spring, summer, and winter. And for acknowledgements, sorry, not acknowledgements, but our research proved that our hypothesis was correct by showing that algae levels are related to both temperature and dissolved oxygen. And there are many dangers that are related to algae blooms. For one, they are toxic to humans and animals. They deplete oxygen, outcompete phytoplankton, and cater to invasive species. So any native species or plants that rely on the bodies of water that are affected by algae blooms will be affected negatively. And this project really showed the relationship between temperature, dissolved oxygen, and algae blooms, and why it is crucial that we research them and help prevent them. So I'd like to thank my mentor, Jesse Scott, for his help, support, and advice throughout this project, especially with the R script, because I had never used it before. And I'd like to thank Leslie McGinnis and Megan Joyce for teaching the class and supporting my project. Here, thank you, and the sources.
Yay! Excellent job. So we're going to look to the chat, and I'll also add up your mentor to see if we have any questions.
Great work, Amanda. You did a wonderful job of correlating this data and assessing the importance of understanding the relation between these water chemistry parameters such as temperature and dissolved oxygen, and how we can use them to better predict harmful algae blooms in the future. A lot of the data that we collected, or assessed, I should say, we didn't necessarily collect, was over a time period in the past few years, but nothing necessarily very, very recently. Do you think if we were to collect data using a real-time data monitoring system, do you think that real-time data would be useful for kind of educating the public about conditions at those locations?
I think it would be beneficial, or at least helpful, especially since there are signs. It'd be helpful for the public to see like the numbers. Maybe it's not like the most complex concepts, but maybe like the algae levels. So if, like in some of the previous graphs, it shows like toxin levels parts per billion. I think that would be helpful so that they kind of see the numbers over time.
Great, thank you.
Oh, and Amanda, I wanted to say I love how what was an observation that you made during COVID just in your daily life ended up turning into this project that can expand through multiple parts of your educational career. And I am really proud about how so many Headwaters students this year have similar motivations for their projects. So it's really cool to see something that you experienced in daily life and then followed through the project.
Thank
So
you.
great job. Okay, I'm gonna get ready our next person. All right. For the last presentation of this session today, we might have a little feedback there. Okay, for our last presentation today, we have Allie Benson, and I'm going to have Sean introduce her.
All right. That's fitting that we go from an algal bloom to a water quality talk. So yeah, it is my privilege to introduce Allie. It's been a privilege to work with you, Allie, this semester. And yeah, we're gonna let Allie take it away. It's you're the expert here, so teach us about what you did.
Thank you so much. All right, let me get the presentation up. One moment. Can you see my screen?
Not yet.
Nope. All right.
But while Allie's loading this, I wanted to mention that we have another session later on this evening that everybody is welcome to join, students from both classes as well as mentors and parents. And that will be starting at 5:30.
If you'll keep giving me a moment. Thank you for your patience.
And thank you for bearing with us. And while you're waiting, I will ask if our fellow mentors would like to share anything from their mentoring experience. Oh, okay, Allie's back.
All right, there we go. Thank you.
And I just added Sean.
All right, thank you. Am I good to start?
Yeah, we'll give Sean a moment.
We're good over here. If
Oh,
she's,
okay,
she's
great. Okay.
All right, thank you. My name is Allie Benson. I'm from Pensacola High School, and my mentor was Sean Leslie from the University of Florida. And my experiment today was called Evaluating Aquatic Contaminants of Heavy Metals and Other Pollutants in Surface Waters Across Urban and Rural Sites in the Pensacola, Florida area. Living above the Florida aquifer all my life has always shown me the importance of water quality, especially in the water that we drink. And I've always been interested in how drinking water and water quality and groundwater quality impacts both humans, animals, and ecosystem health. When most people think of pollutants that would negatively impact drinking water and groundwater conditions, they typically think of manufacturing and industry, fertilizers and pesticides that can lead to hypoxia, and also oil spills. But another uncommon one that is not typically thought of when you think of water quality is automobiles. The asphalt and concrete that they drive on, the brake pads, the tires, and the exhaust that they leave. My research question was, how will the traffic level near a body of water impact the contaminants and pollution found in the site? And my hypothesis was, it is predicted that areas with higher traffic levels will contain higher levels of pollutants than the areas with lower traffic levels. Before I go onto the specifics of each of the sites that I used, I wanted to give a general overview of where the sites are located in relation to each other. So I'm based out of Pensacola, Florida, which is in the panhandle of Florida on the westernmost side of the state, about an hour away from the Florida-Alabama border. The three sites that are medium and then high traffic levels are in the urban area of Pensacola. The purple one, being the low-medium traffic, is near the Pensacola Bay outlet that's connected to the Gulf of America. The green arrow shows a retention pond that's on a major road, and then the orange arrow shows right off the map is a bridge that is heavily used that connects West Pensacola to East Pensacola. The low traffic area was done in Blackwater State Park, which is on the image at the top, and it shows that it is very rural and that there's not very many settlements near there. It looks like it cut it off on my screen, but there's an arrow on the bottom that shows the low traffic sites being Red Rock and Pensacola Bay, and the higher traffic sites being the Retention Pond and Texar Bayou. My methodology. The way that I measured the water contaminants present in the water was the TAP score water testing kit. They sent me two bottles, the large bottle and the small bottle, like you can see on the screen on the left. The large bottle, I used a multi-flush method where I filled it up multiple times before finally sealing it, ensuring that there were no air bubbles. In the small bottle, it contained a little blue tab that activated as soon as water touched it. I used a small cup, flushed it multiple times, and then used it to fill the small bottle. Then I used that bottle of water from this testing site to test the hydrogen sulfide testing strip to test for gas. Most of the sites showed very little hydrogen sulfide gas. Then I stored in a cooler while traveling to make sure that none of the algae blooms and bacteria present in the water impacted the way that the lab would read the results. And then I FedExed the bottles in their original container, which also contained a freezer pack to make sure that they maintained an appropriate temperature. And I tried to keep the time of day a constant when I was collecting for my sites, because when you're looking at traffic levels, doing an experiment at rush hour versus at a time when there's less vehicles on the road can impact the level of contaminants found in the water. The results of my experiment. So of the 54 analytes that I tested, including heavy and light metals, nitrates, phosphates, and E. coli, I found many analytes and contaminants present in the water that were significantly higher than the EPA and the World Health Organization standards. And the general trend shows that increased traffic level and increased urban activity near a site increases the level of contaminants found in those sites. Often there was little discrepancy between both of the medium sites, the low medium and the high medium site. These are also the analytes that I looked at. There's 6 properties, 2 bacteria, which are present at almost all the sites, 8 inorganics, 25 metals, including heavy and light metals, minerals, calcium and magnesium that contribute to hardness, and then calculated parameters. 3 analytes that I really want to spotlight include silver. So silver can enter water through geological sources, but another way that it can enter is through asphalt runoff and collection. Silver can collect onto the asphalt, and then the higher levels of traffic will lead it to run off into local water sources near the road. And it also can enter water through coatings on cars and in soiled silvers and brake pads and tires. The health impacts are that it can cause igeria, which is a skin coloration disorder, kidney and liver issues, and it is toxic to aquatic life. And the graph on the right shows that the lower traffic levels showed very little silver present, and then the medium and then the high traffic areas showed higher silver concentrations. And all three of those sites that showed presence of silver were significantly higher than the EPA guideline for silver, which is 0.1 milligrams per liter. The next one I want to talk about is strontium, which is a heavy metal. It also has geological sources of mineral dissolution, which can cause it to be in water, but it also can be found in trace amounts in asphalt, brake dust, and in tire filler. Its health impact is that it disrupts bone development, especially in children. It also can cause heart and kidney problems and neurological issues. And as you can see in the graph on the right, it was present in the low, medium, and the high sites, which were both brackish waters, as opposed to the low and the high medium traffic levels, which happen to be freshwater sites. But in those sites where it was present, it was 9,974 milligrams per liter above the EPA standard for strontium, which means that anyone consuming that water would definitely feel the effects of the strontium. I also want to spotlight thallium, which is another metal. This metal, however, typically never comes from geological sources and is mainly anthropological sources that it enters water. It comes from cement and asphalt, metallic brake pads, and exhaust from fuel additives. Its health impacts include gastrointestinal distress, neurological impacts, cardiovascular and kidney and liver damage. It is also shown to be higher in the low, medium, and the high sites that were brackish sites, and it is significantly higher than the 0.002 milligrams per liter standard that is set by the EPA. My discussion of all of the analytes that were present, it shows that the analytes that were found are definitely detrimental to human, animal, and ecosystem health, and that there are treatment concerns with having ambient water that can filter into the aquifer, filter into groundwater and drinking water, and that they have such high contaminants that are above EPA standards. And the general trend and increase that areas that are more urban and have more traffic levels versus areas that have less traffic levels having higher contaminants than the areas with less traffic, it supports the theory that of traffic-related water pollution. The limitations of my study, having the differences between the brackish water, which is a mixture of saltwater and freshwater, versus just the fresh water, can impact the way that the pollutants are present. Industrial pollution into the Pensacola Bay may explain the uranium that was found there. The small sample size and was caused by financial constraints. That's why I only collected samples for 3 days in a row at each site. The broader impacts of my study. My study included a water testing of typically untested waters. There's not really some of the places that I did water testing at, there are actually no NOAA sites for testing that water. So those waters are typically untested, and so there is no knowledge or previous knowledge of the contaminants found in those sites. And also the general trend of my experiment supports other papers and theories and the importance of cleaning up local ecosystems. My acknowledgements, I want to thank my dad for transportation and helping me collect samples, FedEx for shipping my packages, Capsule Water Testing Laboratory for giving me my results, Headwaters Meeting Group 2 for helping me brainstorm, Sean Wesley, my mentor, Leslie McGinnis, and Megan Joyce. Thank you.
Awesome job. I'm going to add your mentor also if they would like to ask some questions.
Great job, Allie. Yeah, I do have a question. So we've briefly talked about this, and we both know, being in Florida, our water quality is a joy sometimes to deal with. So what surprised you the most when you started classifying, right, that low, medium, high? I think you know where I'm going with this, right? When we had that discussion, was it surprising to you that those, right, like the low really showed low, but once we diverted from or changed up that traffic, right, we saw a massive increase, just even going from low to high, or your low medium, right?
Right.
Was that surprising to you? Did you expect to see that?
I expected to see more of a linear trend. I guess that I kind of would have anticipated that maybe the higher medium and the high traffic levels would have been closer together, and then the two mediums might have been closer together, which I did see. But I didn't expect the low areas and the low medium and just the medium areas to have such a big discrepancy between those the contaminants found in those sites.
So a good takeaway from this, right, would be we as people, the anthropogenic source really affects greatly, even within a small window of time, how much we can move and transport, right, nutrient and affect that water quality.
Right.
I'd say that's your big takeaway, right? And I think you noticed that, but even with your limitations, I think you still have very important data. Have you thought about discussing with someone else, or maybe bringing this to a step further?
I have actually considered possibly talking to going to maybe my local council or maybe the mayor's office and just talking about like what I found in the water. I was really surprised by the uranium that I found in both of the Pensacola Bay and Texar Bayou, especially because I know that people swim in that water. And although it was lower than the EPA standard, some of the heavy metals, and especially that, was very surprising to find in that water. So
Yeah, your heavy metals were massive. Some of those were large numbers.
And looking at the NOAA sites, there are some in my area, but they're more oriented towards the beach near my area and not necessarily the bay and the bayou. So I think it would be interesting to bring that to their attention.
I was going to say the same thing. That was my question. And I think it would be amazing if you could go, like you said, to the mayor or even a local city council. And I find that people in local government are very, very excited when young scientists in their community come forward and want to participate. And so I think that your data and your presentations would be really well received, and they'd be really excited to hear about it. I mean, maybe not happy about the pollution, but they'd be really delighted to have you.
I definitely will think about doing that.
Reach out to me via email too. I have people at FSU, so we have friends there. So we got backup. But yeah, that's why we bring it up now. So after you've done the study.
Okay, thank you so much. And this is going to conclude the last presentation of our first session. We will have another session that starts at 5:30 p.m. It's 5 o'clock. So students that are joined now, you are more than welcome to join the other group. We'll also have some people coming in and practicing and uploading their slides. And we'd like to thank our audience so much for tuning in to support our young scientists and the hard work that they've done this summer. Thank you again, and we'd love to see you all in session 2. And signing out.